Hello everyone, today our presentation is about a powerful fuzzing strategy named Havoc. It is integrated in many fuzzers as before without further illustration. Our target is to investigate the impact of Havoc. My name is Mingyuan Wu and I'm a joint PhD student from SUSTech and the University of Hong Kong. Lin Jiang and Jiang Hongxiang both are graduate students from SUSTech. Yanwei Huang is from Zhejiang University. Yuxun Zhang is assistant professor from SUSTech, and He Mingcui is associate professor from the University of Hong Kong, and Li Minzhang is associate professor from UIUC. So, the software vulnerabilities are critical since we expose many vulnerabilities each year. Many software bugs have significant impact on the real world. For example, we have a Heartbleed. It impacts 500,000 servers and caused loss of $500 million. Meanwhile, Log4j, which is the single biggest, most critical vulnerability of the last decade. Coverage guide fuzzing has become mainstream to automatically expose program vulnerabilities. We present a typical coverage guide fuzzing framework as follows. First, we have a C corpus, and we select a C from the C corpus. And we pass such C to the mutator to generate a mutant. Then we judge whether such mutant trigger explore new edges or not. If not, it will be discarded. If yes, it will be added into the corpus. A group of fuzzers adopt a random search mechanism, namely Havoc, explicitly or implicitly to augment their edge exploration. The workflow of Havoc is shown in this figure. First, we also select a C from C corpus. Then we use Havoc to generate new mutants. Overall, Havoc enables a mechanism, namely mutator stacking. Havoc first defines a stacking size for the applied mutators for each mutation. Accordingly, Havoc randomly selects mutators into the stack. Eventually, all the stack mutators are applied to the C in order to generate a mutant. Note that generally Havoc enables two types of mutators: chunk mutators and unit mutators. We can see here, unit 1 and unit 3 refers to unit mutators, and chunk 3 refers to chunk mutators. And we will introduce the detail later. For mutator stacking, we can see we stacking the chunk mutator 1 and chunk mutator 4 and unit mutator 10 to generate a mutant. Then things are similar. We also want to judge whether those mutants trigger new edges or not. If yes, they are added into the C corpus. If not, they will be discarded. So for mutator stacking, we actually randomly apply multiple mutators from a finite mutator set to a given seed. We have an example here. First, we apply unit mutators to this seed. Then we apply the chunk mutators to the same seed. Then we combine these two mutators to generate a new mutant. Mutators defined by Havoc can be categorized into two types. So the first type is unit mutators, which it mutate a single bit, byte, or word. And the second one is chunk mutators. It mutates undetermined number of consecutive bytes. So Havoc is integrated in the fuzzers in two manners. First one is the sequential manner. It appends Havoc as a later mutation strategy to the major fuzzing strategy. That is to say, it runs major fuzzing strategy first and then run the Havoc fuzzing strategy second. So for parallel manner, it applies Havoc and the major fuzzing strategy in parallel. That is to say, it runs major strategy and Havoc strategy in the same time, and it requires to synchronize C corpus. Because the power of Havoc has not yet been fully explored, we want to fully evaluate the Havoc by raising two research questions. The first one is, how does Havoc perform on different fuzzers in terms of its default setup and mechanism? That is to say, the default Havoc. So the second one is, how does Havoc perform on different fuzzers under diverse setups? So for our study subjects, we select the fuzzers published in top software engineering and security conferences and we evaluate the fathers within 24 hours for 5 times to get the average results. We select the pure havoc and the fathers with havoc listing here, and fathers without havoc listing here, which it means that the fathers without the havoc as their implementation. And for our benchmark, we have 12 projects commonly adopted by the original papers of our study fathers. And these projects cover 7 different file formats, and the size of these programs ranging from 1,885 to over 120k line of codes. And the programs cover diverse functions, for example, development tool, code processing tools, and graphic processing tools. And for our first research question about the performance impact of the default havoc, and the word original here refers to the original implementation of the study fathers, and the word major here refers to the variant by deleting havoc from the original implementation of fathers with havoc. And integration denotes the variant by integrating havoc with the original implementation of fathers without havoc. So for fathers with havoc, it refers to the fathers which integrate havoc as their default implementation, which is shown here. So we can observe in the result that it indicates that the performance of all the study fathers decrease significantly after deleting havoc. And for father without havoc, it refers to the fathers which didn't integrate havoc. And we also can see the result after appending the default havoc to fathers without havoc. It significantly enhances their original fuzzing strategies. So we can have our first finding. Applying havoc by the default setup can significantly improve the edge coverage performance of the studied fathers. We also present the overall data in this table. Please note havoc here. It means applying havoc only without appending it to any father, that is to say, pure havoc. And the QSIM here, because QSIM enables 3 threads which execute havoc. And this mark refers to the fathers without havoc. So we can see the pure havoc can significantly outperform most of the study fathers, for example, FL, FL++, and use, while obtaining close performance with MOPT and QSIM. So we can have our second finding. Havoc is essentially a powerful father. Executing havoc under 1C without being appended to any father for sufficient time can already achieve superior edge coverage over many existing fathers. So for MOPT, QSIM, and the pure havoc can achieve much stronger edge coverage over the other fathers, and they also have longer execution time for havoc. So our third finding is executing havoc for a longer time upon a father can potentially result in stronger edge coverage performance. In order to investigate the performance impact of havoc on the fathers under diverse execution time setups, that is to say, we also activating the major strategy and havoc respectively run for time duration T, which is 1 hour, 2 hour, 4 hour, and 12 hour in an interleaving manner, that is to say, the modified havoc. So we can see the maximum performance gap of original fathers is 22,401 edges, and the maximum performance gap of interleaved fathers is 2,417 edges. We also have block coverage statics here. We can see after we integrate the havoc into the original fathers, and their block coverage percentage seems similar, looking almost the same. So we have our fourth finding. Executing havoc for sufficient time can dominate the performance of study fathers and significantly reduce their performance gaps. So how do different integration modes of havoc impact performance? So we can see here after the original FL, the gap between the integration version and the integration modes in different setup of time duration. So we can have our fifth finding. As long as the total execution time of Havoc is fixed, how to adapt its iteratively execution can have limited impact on the edge coverage performance of the associated fuzzers. And why does QSIM outperform the other fuzzers by at least 10%? Because the QSIM we mentioned before, it activates 2 additional threads to run the Havoc. And we can see here, we introduce hybrid AND, which means adopt an additional thread to execute Havoc. The hybrid 2 actually also have a significant information improvement, and we can see that also all other fuzzers are catch up with the QSIM. So we can have our 6 findings. Investing more computing resource in executing Havoc can potentially reduce its execution time for approaching the performance bound, but may not be cost effective. Since multiple fuzzers can approach quite close to edge coverage performance, we further attempt to investigate how common their explore edges can be. We determined to adopt a concept of J-card distance to measure the dissimilarity between 2 sets. So in this figure, each bar refers to the J-card distance of 2 different fuzzers. For example, the Havoc QSIM refers to the dissimilarity between the edges explored by Havoc and the edges explored by QSIM. As we can see from this figure, it indicates that applying Havoc to different fuzzers can potentially explore quite common edges. And this is our new finding. Applying Havoc to different fuzzers potentially explores rather common edges, while fuzzers guided by concurrent execution or neural network can better complement Havoc. So at last, we investigate the impact of appending Havoc on exposing program vulnerabilities. To this end, we attempt to collect the program crashes caused by executing the generated seed without appending Havoc to all the study fuzzers. Overall, we derived 256 unique crashes from a total of 879 crashes, where 243, which is 95%, are exposed by Havoc, and only 13 are exposed by their original fuzzing strategies. So we have our 8th finding. Havoc can also play a vital role in exposing potential program vulnerabilities. So note that as a simplified mutation strategy, the mutator stacking mechanism containing 2 steps: determining stacking size and randomly selecting mutators to impact the performance of Havoc. We then investigate the performance impact caused by each step. We first attempt to investigate the performance impact of stacking size and implement Havoc and a fixed stacking size for its mutation. And this figure presents our evaluation results of the edge coverage ratio results in terms of all the possible fixed stacking size. That is to say 2, 4, 8, 128. On top of all the study benchmark projects, we can observe that overall, the stacking size which causes the optimal edge coverage performance for each study project can be quite divergent. For example, selecting stacking size A2 and 32 can optimize the edge coverage in TCP dump, DJPAC, and mu2 respectively. And next, we uniformly select a chunk mutators or unit mutators and then randomly select their inclusive mutators under the given stacking size for mutating one seed. And this figure presents the edge coverage ratio results in terms of the selected mutator types on top of all the study benchmark projects. We can observe that overall, the distribution of the edge coverage ratio performance can be quite divergent among different projects. For example, the edge coverage ratio of the unit mutators ranging from 18% to 94% in the XML int and TIFF2BW. According to our previous result, it is essential to adopt the selection of the stack size and mutator types for different projects to optimize their respective edge coverage performance. As a result, we propose Havoc map. Map refers to multi-unbanding, and we use UCB1 tune algorithm to optimize it. And we also have a C corpus, and we select C from the C corpus. Then we're using the stacking size banding to select a specific stack size. And we have a mutator level bandits to enable two arms representing trunk and unit mutators. So after determining the stacking size, the mutator type bandit will select the mutator to fill in the stack. We can see here we fill in the stack. Then we generate a mutant by the stacking mutator, and we execute the mutant on the target program. After executing on the target program, we use the coverage information to update our bandits. And if we hasn't explored any new coverage, the mutants are discarded. Otherwise, they are added into the C corpus. So we can see here, because the QSIM has 3 threads, we also adding 2 additional Havoc threads to construct a variant named Havoc 3 map, which executing Havoc map in 3 threads in parallel. So we can observe that Havoc map achieves significantly better performance than pure Havoc, that is to say, increasing the average edge coverage among all the benchmark projects by 11%. On the other hand, executing Havoc 3 map can result in 9% edge coverage gain over QSIM. Since QSIM has 3 threads in parallel, such a result altogether can demonstrate the strength of our proposed Havoc map. And this figure presents the edge coverage trend of our study approaches upon each benchmark for 24-hour execution. Overall, Havoc map outperforms pure Havoc in most of the benchmarks significantly. Moreover, Havoc map can outperform QSIM by at least 10% in terms of edge coverage on 5 projects, while incurring rather close information on the rest projects within a single thread. So here's our contribution. First, we conduct an extensive study which studied the performance impact by applying Havoc to a set of study fathers on real-world benchmarks, and we find that applying Havoc can substantially improve the edge coverage and crash detection for all the study fathers. And we also have a technical improvement. We propose a lightweight approach Havoc map based on our findings, which can boost the pure Havoc and outperform all the other study fathers. And we also have some critical guidelines. We highly recommend future research to investigate more powerful techniques for combining Havoc, concurrent execution, and learning-based fuzzing. Okay, that will be all. Thanks for listening.